In 1994, a mathematician wrote a 9-page paper. Since then, the US government has budgeted $7 billion to change the encryption on all your data, whether it be on your iPhone, your bank details, encrypted messages, because of it. Your iPhone was quietly re-engineered because of it. The wild part, the paper only acts on a machine that doesn't exist yet. Starts with a guy wanting to solve problems that had absolutely zero world use whatsoever. So, typical mathematician. Set the scene. 1994, New Jersey. Peter Shor is about to give us something known as Shor's algorithm, one of the basics of quantum computing for 50 years in the future, one of the foundational concepts that will take us further. The research lab he's at has given us the laser, the transistor, the Unix. Little did he know he would be adding to this. But right now, he's not even working on code breaking. He's just going to talks. So at the time, they still had the same issue. There were unbreakable problems that quantum computing could theoretically solve. One person that was working on this was a guy called Charlie Bennett. Quantum cryptography was the study of using quantum physics to send unbreakable secret keys. What Charlie Bennett asked was, can you prove that what you're sending is secure? Shor originally tried, but then he gave up. Until 1992, a scientist, Umesh Vazirani, presents, instead of sending an unbreakable quantum key, the opposite. What if a quantum computer can solve a classical problem better than a classical computer can? And the trick was, this problem actually had zero world use. It wasn't a classical problem that people interfered in real life, it was artificial. Computers were useful for something. They could beat classical computers at something at least. So now Shor, working for Bell's lab still, walks away with one question. Can quantum computers beat classical ones at something useful? Quick disclaimer, at this point, quantum computers actually did not exist. Not even teeny tiny ones. No one had built a single qubit at this point. The entire field was people doing maths on an imaginary machine. What Vazirani had done was build a quantum Turing machine. What this was a precise mathematical model running on quantum computing rules, and then proved theoretically that it would beat a classical machine at this specific classical problem. So it's giving made up problem, made up model, made up solution. Everything's very theoretical right now. No wonder Shor wanted to see if it had applications to the real world. Simon submitted a paper to one of the largest computer science conferences at the time, 1993. His paper was essentially about a guessing game. Imagine a locked machine. You feed it a number, it spits out an answer. Feed it another number, it spits out another answer. But you can't open it up and see what it's doing on the inside to the original number. The secret in this is that for some numbers, matching pairs, they would give the same outputs. And which number it was isn't random. They'd be related by the same individual number every single time. This was known as the hidden number. So Simon, being super creative, called it the hidden number problem. So great, maybe the number's like 10, maybe it's 18, maybe it's 2. No, this machine takes numbers that are hundreds of digits long. This makes it really difficult for classical computers to solve. And what Simon proved, a quantum computer can do it almost instantly. Let's take what a classical computer would do. Hundreds of digits long, it has no shortcut essentially. It takes every single number and feeds it in one at a time, hunting for two that would match. With inputs that size, there would be more attempts than atoms in the universe. This is what quantum computers can do. Instead of taking one input at a time, they can essentially sense all the inputs at once. And here lies what quantum computers are good at. They can find one hidden pattern in an astronomically large haystack. Let's talk about something you use every day, the internet. What's protecting the internet? How is it private and secure? The headline is Public Key Cryptography, known as specifically RSA. And this would be every padlock on your browser, every card you've ever entered, every encrypted message, it's all protected by this. RSA security rests on one huge bet. Take two huge prime numbers and multiply them together. You can find the result pretty easily, it's just multiplication. But the factoring back down to the primes and finding the original two from such a large number is difficult. The same issue from our classical computers applies here. In fact, a classical computer we need longer than the age of the universe for the number sizes that banks use. But actually, isn't this sounding a little familiar? A process where there's a pattern with really large numbers that a classical computer will find really hard to do, But maybe if we could kind of sense them all at once, the pattern would become really clear. Oh my God. This is a version of Simon's problem that he showed quantum computers can solve easily. Exact kind of thing quantum computers would demolish. So this is what Shor gets to work on. Simon's problem worked on a mathematical space. Shor now wanted to attack real encryption. He first tried this with a minor version of the problem, with a different type of encryption problem known as a discrete log problem. Cracked it. He told almost nobody at first. You don't go around announcing, hey, I've almost broken the internet's encryption, unless you're sure. The only people he told were his boss, who helped him solve one minor error in it, a colleague, and then an internal seminar at Bell Labs where he worked. Days after that seminar, he solves RSA factoring. The lock on absolutely everything is now breakable. The catch is, on a machine that doesn't exist yet. That same weekend, he gets a call. Who is it? Vazirani, OG believer that quantum computers could solve problems quicker than classical computers. Of course, he's interested now there's a real-world application. He says, hey, I hear you can break down factors on a quantum computer. Tell me. But Shor didn't tell anyone. How'd this tea get out? In fact, he's going to conferences, he's presenting awards, he's doing his job and living his life. And suddenly people are coming up to him and asking him about this algorithm. But really, the most key thing that Shor's algorithm had done was put a ticking time bomb on all encryption. The idea that all encryption was breakable, everything on the internet was prone to shutting down, and all privacy was going out the window, it just rested on physical hardware being created, had come from one mathematician. But remember, there's a reason he didn't want to put this out. He was using caution. He wanted to make sure there were no flaws in his theory before coming out. Well, a physicist at IBM found one of those exact flaws. In 1994, Rolf Landauer. But the thing is, he's not saying Shor's maths is wrong. He's just saying the machine that it needs to be built on can never exist. It's not possible. Qubits are the basis for all quantum computers. Landauer was suggesting that qubits are essentially too fragile. Heat, vibration, stray fields, everything corrupts them. One way classical computers survive this noise is by copying information. However, this can't be done on quantum computers. Quantum mechanics has a law known as the no cloning theorem. This means that you can't copy an unknown quantum state ever. And because of this, the way that classical computers would correct the errors that they have, copying information, quantum computers can't do that. No copying means no error correction. No error correction means errors just pile up. Errors just piling up means computation don't work. For Shor's algorithm to physically work, it would need billions of operations with a B, and they would have to be essentially perfectly executed. At the time in the 90s, they had around 80% accuracy. So where does this leave us? People around the time start thinking Shor's algorithm is one of those beautifully theoretical things, but doesn't have physical legs to stand on. Kind of how we see string theory nowadays. And after about a year, people start thinking Landauer was right. Shor won't make this exist. He made physics for something that we can't physically prove. Shor goes away. He goes to his little mind palace and he starts thinking, okay, so I have an algorithm here. And what needs to change? What needs to be different so that this algorithm can actually work? I need qubits to be able to correct errors. The way that we would correct errors in classical computing, we needed an alternative to come to quantum computing. And we know cloning isn't an option. So let me think, what can I do to make this happen? And then my algorithm will have something to run on and it will be proved usable. I didn't work that hard to get nowhere. He finds a loophole. You don't copy one qubit to another. You spread one qubit's information across 9 different qubits. Here you should know the difference between qubits, quantum computing, and bits, classical computing. In one sentence, bits are zeros or ones, either or pieces of information. Think of qubits like a recipe, a blend. Maybe they're 30% zero, 70% one, something like that. That blend is the information that qubits carry. Cloning would mean 9 different qubits, each holding that same recipe, that blend, that superposition. However, what Shor did was write one recipe in bigger ink. 9 particles still in sync with each other. They all hold that same blend, that superposition. The key here is that it just no longer lives in one single particle, and all 9 of them are entangled. What that mean? Well, if one gets corrupted, the other 8 are still there to let you repair it. This is quantum error correction. Man just invented an entire field of physics. It is the reason that Google, IBM, and other big tech institutions and scientists all believe that quantum computers are possible to be built. Same guy started out not thinking about cryptography, ended up creating an algorithm that could theoretically break the entire internet's future, then was proved wrong, then decided, hey, I'm gonna work harder on this and prove myself right, and then saved quantum computing's future. Okay, let's talk about applications today. Why should we care? Why do we care about this? Well, the machine that runs Shor's algorithms doesn't actually exist. Algorithm's still sitting there waiting since 1994 to catch up. Governments aren't waiting for it to happen either. There's been a big push towards taking data that's encrypted in RSA right now and putting it in a method that's safe for post-quantum decryption. Every major cloud for that exists is currently switching to quantum-resistant encryption. Your iPhone in your hand, it's being protected against Shor's algorithm. It's being protected against a computer that doesn't exist yet. IBM's first targets for a machine that will not have these errors, be error tolerant, or as quantum scientists would call it, fault tolerant. Nobody knows the date of when it will happen, but everyone knows that it's coming. And in fact, the defense is already happening. The US has set a hard deadline of 2035 to replace all its cryptography and is spending approximately $7 billion on the process of doing so. All because of one paper written by one guy who first broke the internet's privacy and then proved quantum computers could exist. That is the impact of Shor's algorithm. Today we learned a lot, today we handled a lot. I think the biggest takeaway from this is a practical application of quantum computing. How can we go from the idea of entanglement and particles being entangled together and then present a real world application? Well, entanglement leads to qubits, qubits lead to quantum computing. Quantum computing is only possible because of Shor's algorithm and his processes with encryption. See you again for the next one, so subscribe so you don't miss it or something.